All right. And start talking.
Everyone making it through midterms all right?
No.
Yes, no, no. Okay.
I think it's midterms. Am I all right? Two very good questions.
Yeah.
Not if I have anything to do with it. All right, so here I am to tell you about the P-adic numbers. So these are an object that is generally thought of as being something that kind of intrinsically comes from number theory, but as you'll see, there's sort of a lot of analysis and to a similar extent topology, although I won't talk about it as much because I sort of try to, segregate all of the really complicated things and just sort of mention them at the end in a rapid fire lightning round kind of activity. So let me give you the outline, which is not completely accurate, but you can complain about it at the end if you like. All right, so first I want to motivate the P-adic numbers and where they come from and why number theorists like me care about them with some totally illegal calculations with infinite series. Okay. And then the theme for most of the rest of the talk is to explain how, in fact, I can make some extremely illegal infinite series calculations into things that are 100% correct, which is always very satisfying. So that will give me the motivation for defining the P-adic numbers. Then I will actually give the definition. And I will try to silo a little bit of the analysis that has to go into that, but it's sort of baked into the definition. All right, and then I will hopefully be able to tell you some uses that the P-adics have in number theory and the kinds of problems that motivated their development in the first place. Okay, so let's start out with a nice relaxing geometric series. 1 plus a half plus a 4 plus an 8 plus a 16, 1/32, etc. Right? A nice, easy, infinite geometric series. Okay. So as I would hope most everyone has seen this series before and knows what the sum is, right? If you add these up, this converges to 2. So if you just write down the partial sums, you can just write down a formula for it. It's 2 minus 1/2 to the n. If the last term of the sum was 1/2 to the n, so that converges to 2. All right, but let me give you sort of the way that one usually works out this infinite series sum by just manipulating it. So if I take this series and divide by 2, in other words, multiply each term by a half, what I get is 1/2 s is 1/2 plus 1/4 plus 1/8 plus 1/16, and so forth. And then if I just take s and I subtract a half s, all the terms after the 1 cancel. Right? I have a half minus a half, a fourth minus a fourth, an 8 minus an 8, and so forth. And so I see that s minus a half s is 1, so s is equal to 2. All right, so I imagine many of you have seen the derivation of the sum, the formula for a geometric series done exactly this way. Now, this works if I give you the more general one, 1 plus r squared plus r cubed. If I call that s multiplied by r, then it just shifts all the terms forward by 1. So if I subtract s minus rs, I get 1. And so s is 1/1 minus r. Okay. Now, you may quibble that there's some issues that happen if r is equal to 1, but there's issues that happen with lots of values. Okay, so this is the kind of sort of live manipulation of infinite series that mathematicians and others did for hundreds of years without worrying even a tiny bit about whether they were legitimate. Okay, and it was only until the mid 1800s when mathematicians were doing things with Fourier series and really trying to nail down a bunch of stuff carefully that they discovered, oh yes, there's some serious philosophical disagreement about what a continuous function is, for example. And it all had to do with sort of manipulations of series like this without being very careful about whether this kind of calculation is actually legitimate. Okay, because this calculation is only okay if the series actually exists, if the sum actually exists, right? If the series actually converges. Now, technically, the asterisk would be you needed to converge absolutely in order to rearrange the terms of the series and do the cancellation the way that I did. which for this series is not so hard. You just put absolute values in the terms and sum them up, and it's the same series except with the absolute value of r. So it's not really a big change. Okay. And so you can just check that the series only converges if the absolute value of r is less than 1. If the absolute value of r is equal to 1 or greater, then the series does not converge. Like the terms don't go to 0. All right. And so it's completely illegal to plug in numbers whose absolute value is bigger than 1, like 2 or 10 into this formula. So let's do that. Okay. So what happens if you set r equals 2 in this formula? What does it say? 1 plus r squared plus r cubed r to the 4th, etc. is 1 over 1 minus r. So I get this. 1 plus 2 plus 4 plus 8 plus 6 is equal to negative 1. Okay. Pause here for the audience to. Oh wait, no, I should. Okay. Okay. But so you know, audience participation, if you like. Tell me several reasons why this is complete bullshit.
Some positive terms, like a negative.
Yeah, I'm summing a bunch of positive numbers and I'm getting a negative number. That's sort of the biggest problem with this, right? That's obviously something that is an issue. Yeah.
Totally flies in the face of what we typically define as convergence.
Yes, sure. The thing on the left-hand side does not converge. So, I mean, for me, you know, I'm okay with saying that the left-hand side diverges to infinity, or you can sort of make it more precise in saying that it goes to positive infinity. That's something that sort of would make sense. But certainly whatever positive infinity is, I'm pretty sure that it's not equal to negative 1. All right, so there we go. That's what I said. So there's absolutely no scenario in which this calculation could possibly be correct, right? That's the philosophy. And then the whole point of this talk is to show how you can make this correct and make this a completely legitimate, correct statement. The equal sign is okay. Everything about that is fine. So this one is a little bit harder for me to do it because I have to do things in binary. So let me instead do r equals 10 and make this sort of even more disgustingly weird. So now if I said r equals 10, I get 1 plus 10 plus 100 plus 1,000 plus 10,000 is 1 over 1 minus 10, which is negative 1/9. Okay, so now you're supposed to express even slightly more shock and horror.
So on the left, we have a number with infinite ones.
Yes.
On the right, we have negative 1/9.
Yes. So why do I say slightly more? What's even worse about this one than the one I had on the last slide? Yeah.
This is so clearly like expressible in like base 10 that, you know, having this like minus 1 over 9, which I think is some ugly like repeating fraction or something.
Yeah.
To be fair, it's also expressed in infinite ones.
Yeah. So I mean, there is something kind of curious about that, right? I mean, if you write out 1/9 as a decimal, it's like 0.1111111 repeating. That's sort of what that thing on the other side is, right? I mean, sort of. I mean, I guess. Yeah. But you know, what I was going for was like, okay, this is at least okay, fine. It's integers. It's some weird sum of a bunch of positive integers gives me a negative integer. But how the heck can I get something that's not an integer as the sum of this? That's even more.
Oh, wait, by integer closure, that's so problematic.
Yeah, that's really a problem. That's even less logic. Okay. Right, because you know, I can get behind saying like, okay, maybe this is true like mod something or whatever. You know, because like then I can have like 8, you know, 1 plus 2 plus 4 is congruent to, you know, negative 1 modulo 8, for example. That's true. This, what is this nonsense? Okay. All right. So let me fix that, make it an integer. I'm going to multiply by 9. And I have 9 plus 90 plus 900, 9,000, 19,000, etc. going on forever. That's back to equaling negative 1 again. All right. Still just following along with me here. I like it. All right. So let me be as charitable as I possibly can in trying to interpret what this thing on the left-hand side is. Okay. If that means anything at all, it should be the limit of the partial sum. If I just add up the first bunch of terms and then take the limit, that's what the sum on the left-hand side should be. So what are the partial sums of this thing? 9, and then I add 90 to it to get 99. Then 900 gives me 999. And then 9,999, and then 99,999, and then 900. Okay, you get 999, right? Just like strings of 9s. So the limit, if you're willing to go that far with me, it's just gonna have nines that just keep going. Like this. I made it run off the slide too, it's fun. For emphasis, right? It starts over here, right here. Units, digit, 10, 100,000, 10,000, 100,000, right? Just nines. Going on forever to the left. So, the ludicrous claim is that this number is equal to -1. Well, how do you tell if a number is -1? This is the philosophical question I ask my intro to math reasoning students.
Additive inverses.
Yeah, you add 1 to it, right? That's exactly what you do, and hope that you get 0. So let's try that. Okay. Everybody knows how to do addition, right? Okay, so do it. All right, so 9 plus 1 gives me 0, 0 with like a 1 that carries, right? Okay. Great. And now, all right, so now I add 1 plus 9, and that gives me 10, so I get another 0, and it carries. And then I add 1 plus 9, and I get 10, and it's 0, and it carries. And I have 1 plus 9, and I get 0, and it carries. Okay, let's just keep going, right? Okay, so here's 10 more steps, and then there's just like, right, it's clear what happens, right? It just keeps going forever. So I just get 0, 0, 0, 0, forever.
You can't tell me the universe has rollover.
Hey, look, I'm not going to argue with the computer scientists about integer overflow, okay? Like,
You're saying it's infinity plus 1 to 0.
I'm not saying anything of the kind. I'm just sitting down and doing elementary school arithmetic right here. Okay. Okay. So here looks like if I add 1 to this infinite string of 9s, I get an infinite string of zeros. And if an infinite string of zeros means anything, that had better be 0, right? Because it would be 0 times 1 plus 0 times 10 plus 0 times 100 plus 0 times 100. It's 0. Okay. I mean, I don't care how many zeros you try to add up, you're still going to get 0. You can add up uncountably many zeros if you want. It's still 0. Right? So if I add 1 to that thing, I get 0. So subtracting 1 tells me that 9 plus 90 plus 900, 9,000, etc. is -1. Okay. So now the question is, is there some way in which I could make that a meaningful, like this calculation is actually legitimate? Right?
Beyond what we already showed.
Now, mental exercise for you. Redo the same thing for the powers of 2 and just do it in binary. Right? Because what do you get if you write these in base 2? This is 1, and then this is 1, 0, and then 1, 0, 0, 1, 0, 0. And so when you do the partial sums, it's all 1. So then you add 1 to that, 0, you carry it 1, it's 0, 0, right? Same thing, but just with 1s. And so it works the same way for the sums of the powers of 2. It also seems like if you could do this formal calculation, then it works out. So, all right, so what I would like to do now is to try to get you to a place. This is a pun, but nobody knows that it's a pun, the word place. Get you to a place in which that infinite sum actually converges. Right, because that's the problem. 1 plus 2 plus 4 plus 8 plus 16, etc. That doesn't converge in the usual land of real numbers, right? The terms get really big. So what I'd like to do is I'd like to find some other way of measuring the size of an integer, where instead of getting big, those terms get small. Why would I want that? Well, remember back in Calc 2, when you learn about how to sum infinite series, if you haven't taken Calc 2, remember forwards in time to when you will learn that in the future. And so there's a bunch of series convergence tests, which I don't care about at all. I only care about like the very first one that they teach you that has some silly name like the nth term test or something like this. And so the point is, the very first thing that you learn when you learn about infinite series is that if you want an infinite sum to converge, the terms have to go to 0. If the terms don't go to 0, then the thing definitely can't converge. Now, okay, the bane when I am teaching Calc 2 is then that students don't internalize the fact that the converse of that statement is false. Namely, if the terms go to 0, the series can still diverge. Okay, take the harmonic series, 1 plus a half, right? The terms go to 0, but the sum still goes to 0. Okay, but this one is okay. If I want the sum to converge, the terms had better be going to 0. Now going to 0 how? So what I mean is I mean the size of the terms are getting small. Okay, I'm sort of like taking like 1/2 a step back from like just saying the terms go to 0. I want them to get to get small in size. All right, so what I want is I want to measure the size of an integer in a way that the powers of 2 have small size, the bigger the power I take. Now, how could I make this work? Well, I could just define some stupid size function on the integer such that like the size of 2 to the n is like, I don't know, 1 over 2 to the n or something. And then just, okay, great, now the powers of 2 have small size, so I can just add them up and it converges. But of course that's, like if I just do some stupid function, like why would I expect this to make any sense? I want whatever the size function telling me how big an integer is, I want this to have some nice properties. Otherwise, there's no point to it. Okay. Right? The whole point is that I'm trying to develop some kind of theory that actually makes sense and is consistent in some way. So what kind of properties do I want on my size function? Well, let me give you a size function on integers that already exists. The absolute value. This one, probably pretty familiar to you. If you like, if you're not super happy with absolute values of integers, then just think about absolute values of real numbers instead, or rational numbers, or whatever. Okay. So that absolute value, of course, the whole point of this discussion is that it does not have the property that if I take the size, in other words, I apply my function to 2 to the n, that gets small, because those numbers get big. All right. But let me give you some other nice properties that are sort of a suggestion of what sorts of things I might be looking for. Okay. So first of all, if I take the absolute value of something, it's always positive, except at 0, when it's 0. All right. This is the kind of thing that is sort of sensible because it helps you like detect 0 with your absolute value function. Second, really usefully, the absolute value is multiplicative. The absolute value of a product is the product of the absolute values. Now, okay, for real numbers and integers and rational numbers, this isn't really so exciting. But it's also true for the absolute value of complex numbers too, which is another sort of notion of size function that is good to think about. All right. And then the other really important fact about the absolute value is that it satisfies the triangle inequality. This is the other really fundamental fact about it. Right? The length of the sides of 2 sides of a triangle is greater than or equal to the other. And that's what this says. Okay. So 3 properties that would be kind of sensible to man if I'm trying to come up with some new size function on the integers. All right. Well, great. So can I cook up an absolute value like function? I put like a 2 under it to keep it separate from the regular absolute value. Yeah, I know it's a very helpful thing, but yeah. But it's the second one. It's the second one that I'm talking about. That's why I hesitate there. Okay. And I wanted to have these 3 properties. So first, I wanted to always be greater than or equal to 0, and I only wanted to be 0 when I plug 0 into it. Second, I want it to be multiplicative. Okay, so if I take the absolute, this new absolute value of a product is the product of the absolute values. And finally, I wanted to obey the triangle. But also now, I'm going to insist that the size is, I forgot. And the sizes of the powers of 2 go to 0. And if I do that, then I at least have some hope that maybe I could use this absolute value to actually add up this sum, 1 plus 2 plus 4 plus 8 plus etc. It at least is not going to be completely ludicrous on its face. All right, so what should I do? Well, it's multiplicative on any integers. I just sort of decided that. So that actually imposes quite a lot of things because, for example, if I want to do the absolute value of 6, this had better be the absolute value of 2 times the absolute value of 3. And so in particular, the absolute value of 1 should be the absolute value of 1 times itself. So the absolute value of 1 had better be 1. Because if it's 0, everything is 1 times itself. So the absolute value would be 0 on everything, which would contradict item number 1. So I want like the absolute value of 1 to be 1. And I want it to be multiplicative like this. So for example, if I wanted to compute, well, what's the absolute value of, I don't know, some number, 81. Well, that would have to be the 4th power of the absolute value of 3. And so in general, if I just look at the prime factorization of my number, all I need to know is what this absolute value function does on the primes. And if I know that, I can compute the absolute value of everything else. I mean, I also need the absolute value of -1, but it comes from this, that it has to also be 1 as well. Okay. So what should I do on the primes? Well, what's the first prime? 2. What should I do? What should I take the absolute value of 2 as? Remember, I want this to go to 0. So what would be a good choice? Something less than 1, right? Because the absolute value of 2 to the n would be the absolute value of 2 to the n. And if I want that to go to 0, something less than 1. Okay.
1 over the absolute value.
Well, if I did 1 over the absolute value, it turns out not to satisfy the triangle inequality. Yeah, it's a good try. I like it, but no, it doesn't work. It's a good try. So, sadly, it's just not quite so simple. All right, so let's just start with 2. What value should I pick for the absolute value of 2? Something less than 1, I don't know, 1/2. Halfway between 0 and 1. Something not too big, not too small. All right, so let's take the absolute value of 2 to be 1/2. And then the absolute value of 2 to the n would be 1 over 2 to the n. That certainly goes to 0. Goes to 0 very fast. In fact. Okay. What should I do with the other integers? What should I do with the absolute value of 3? Absolute value of 5? All 1. Well, I like that idea. It's very lazy, which is why that's what we're going to do. This is the laziest thing that I could think of. Just take all the other primes to have absolute value of 1. Now, as a matter of fact, like this turns out to be the only thing that you could do that actually will satisfy the triangle inequality, but secretly you don't know that yet. Right. But you say, all right, let's do the laziest possible thing and just see if this works. Okay, so what I do is I declare that the absolute value of 2 is 1/2, and the absolute value of every other prime is 1. And so that completely determines what the absolute value of every other integer has to be. I could just write it out in terms of the prime factorization.
Which makes it 1, yeah.
Yeah, so what I do is I just take out the power of 2 from my integer and write it as a power of 2 times an odd number. And then it's just 1 over the power of 2. That's it. And then I also have to define what the absolute value of 0 is. The absolute value of 0 isn't determined by this information, but it has to be 0. Like there's nothing else sensible because that was item number 1. If I have the thing equal 0, then it should have absolute value 0. Okay. So it has an attractive simplicity to it, I will say. Does it satisfy the requirements? Well, let's go. Number 1, is it always greater than or equal to 0 with equality only when the element itself is 0? Yeah, that's pretty obvious, right? Every non-zero integer will be 1 over some power of 2. And 0 goes to 0. Is it multiplicative? Well, yeah, that was the whole point. Like it's multiplicative just from the prime factorizations. Okay. Does it satisfy the triangle inequality? Well, that's the unclear part. Let's find out. Okay, so how do you decide if something is true? You do a bunch of examples and you see if it works. This is a great philosophy of how to do math. Okay. It's what I tell my students in all my classes when I remember to tell them how to do anything. Like when I'm trying to help them. I say work out some examples and see what happens. Okay. And the great thing about doing examples is if the thing that you're trying to prove is false, hopefully you will see that you just get a counterexample. And if it's true and you see that it's true for every single example you do, that might give you some help about why is it true. Okay, so let's try this out. So I put all the definitions up at the top of the slide so that you could do this calculation yourself. Okay, so let's see. If a equals 1, what is the absolute value of a under my special absolute value number 2? Yeah.
Sorry. I didn't need to answer.
Okay, all right. Yeah, 1, right? Because if my number is odd in general, right, then k is going to be equal to 0, and so I just take 1 over 2 to the 0. So the absolute value of an odd number is 1. The absolute value of an even number, divisible by 2 but not divisible by 4, is going to be 1/2. Multiples of 4 but not 8, it's going to be 1/4. Multiple of 8 but not 16 is 1/8, and so on and so on. Okay, so if a equals 1 and b equals 3. Absolute value of a is 1. Absolute value of b is 1. A plus b is 4, so its absolute value is 1/4. So I ask, okay, does this work for the triangle inequality? If I take 1/4, is that less than or equal to 1 plus 1? The answer is, yeah, by quite a lot. All right, how about a equals 2 and b equals 7? What's the absolute value of a? 1/2. What's the absolute value of b? 1. Okay, and then a plus b is 9. What's the absolute value of that? 1. Okay, so if I have 1, is that less than or equal to a half plus 1? And the answer is yes. Okay, a equals 2, b equals 4. Absolute value of a, 1/2. Absolute value of b is 1/4. A plus b is 6. What's the absolute value of that? 1/2. 1/2 is in fact less than or equal to a half plus a fourth. Thumbs up. All right. How about a equals 4 and b equals 4? Absolute value of a, 1/4. Absolute value of b is the same because it's the same number, 1/4. Absolute value of a plus b, 1/8. Is 1/8 less than or equal to 1/4 plus 1/4? Yeah, sure. A equals 4, b equals 12. Okay, so again, absolute value of a is 1/4. Absolute value of b is 1/4. Absolute value of a plus b, because that's 16, is 1/16. 1/16 less than or equal to a fourth plus a fourth? Why, yes, it is. Okay, I mean, I could just keep doing this all day, but
It's whenever you're adding two that have the same factor.
yeah, okay, see, this is the thinking that you should be like, okay, it has something to do with sort of just like how the powers of two seem to relate to each other.
So you add them.
Yeah, okay. All right. And then 8 and 8, all right, again, I just skipped. A plus b is 16, so 1/16 is less than or equal to 1/8 plus 1/8. And then, okay, fine, I picked some numbers that were large enough to not have me wrap over one line. So this kind of constrained me a little bit. Okay, so if a is 40 and b is 80, absolute value of a is 1/8. Absolute value of b is 1/16, and then a plus b is 120, which is absolute value 1/8. So yeah. So not only is this true, there's actually a much stronger statement hiding here, which is, right, if you look at the absolute value of a plus b and just compare this to the two numbers, don't even add them together. 1/8 versus an 1/8 and a 16. 1/16 versus an 1/8 and an 8. 1/8 versus a fourth and a fourth. 1/2 versus a half and a fourth. In fact, the absolute value of the sum is always less than or equal to whichever one of those is bigger. It's less than or equal to at least one of the two. Always. It's not just like I don't even have to compute the sum. I just look at whichever one is bigger. And that gives me a bound on the opposite value of the sum. All right. So let me prove that. So here's my absolute value function, 1/2 to the k. All right. So the absolute value function is 1/2 to the k if my number is 2 to the k times something odd. So the claim is actually that for any integers a and b, the absolute value of the sum a plus b is less than or equal to the max of the two absolute values for a and b. Prove it. Well, just factor out the powers of 2. So one exception is, of course, I have to always do a or b equals 0 separately because it has its own like thing here. So why is this true if a is equal to 0? Well, if a is equal to 0, this is the absolute value of b, and it's supposed to be less than or equal to the maximum of 0 and the absolute value of b, which is dumb, right? Because that's just going to be the absolute value of b. Likewise, it's symmetric in a and b, so it works if b is 0. Okay, so now suppose they're not 0, and then just take out the factors of 2 for each one. So a is some power of 2 times some odd number, b is some other power of 2 times some other odd number. And just by switching the two numbers, if I need to, I can assume that a is the one with the smaller power. Well, it's less than or equal. So the exponent for a is less than or equal to the exponent for b. Okay, so then the absolute value of a is 1/2 to its power. Absolute value of b is 1/2 to its power. And so the maximum of this is whichever one of those is bigger as a power of 2, but it's the exponent is negative, it's the one with the smaller exponent. So it's 2 to the minus ka. Now, what happens if I add these together? Well, 2 to the ka times qa plus 2 to the kb times qb. I can factor out 2 to the ka for both terms because it's certainly in this one, and it's also in this one because the exponent here is at least as big. So if I do that, I get 2 to the ka times some stuff. The integer for a plus some power of 2 times the integer for b. And then I just say, well, hey, wait a second. I don't really need to compute the exact power of 2 here. All I need to do is observe that it's at least this power of 2 that's sitting right here. Because this is the power of 2 times an integer. And so the power of 2 dividing a plus b is at least 2 to the ka. And so that means that it's size with respect to this thing is at most 2 to the minus k. Because if I have a bigger power of 2, then this would get even smaller. So the smallest possible power of 2 I can have is this one that's here. And well, hey, wait a minute, that's exactly the maximum. So there you go, done. Okay. And in fact, you get it like, I mean, this is already way stronger than the triangle inequality, but you can make this even like slightly more precise, which is that if A and B have different absolute values, then actually the absolute value, then I get equality. And the reason is that this is an odd number plus some power of 2 that's positive and something. So it's also odd. So in fact, if the powers of 2 showing up in A and B are different, then I have the same exact power of 2 in the sum. That's what I'm saying. So the point is that here, absolute value of A and absolute value of B are different. And then the absolute value of the sum is just whichever one of these is smaller. 1/8. Okay, so absolute values, good stuff. Lets me decide how big some integers are in a strange way. All right. So what was the point of this? Now that you're like thinking about sizes, the point is I can give you a different absolute value function on the integers, such that the sort of powers of 2 as I take bigger powers have size going to 0. And so now the plan is to make sense of this infinite sum 1 plus 2 plus 4 plus 8 plus 16, etc. All right, but you're gonna have to wait like 2 more slides because I want to point out something that should be kind of obvious, but this had nothing to do with the number 2 specifically. I could do any prime number in place of 2. I could do it with 3 or 5 or 2027, which is the next prime after this current year. Fun fact proves that that's prime, not quite so easy to do. And if you want to learn how and haven't already taken number theory 1, come take number theory 1 with me in the spring and I will teach you how.
It's a really easy way to prove it.
Yeah, get it, like ask Mathematica if it's prime.
Oh, well, that too.
Yeah, that's how everyone does it. Yes. Okay. All right, but the point is I can do it, I can write down a similar P-adic absolute value. I finally will tell you the name of this thing. The P-adic absolute value. What it is for 1 over P, for P, it gives the value 1 over P, and then at all the other primes it's 1. And so the idea is that sort of in some sense it kind of pulls out the information with respect to just that prime P and ignores everything else. And so by the same exact proof that I gave, if you just put P in place of 2 everywhere, then you get all of these nice absolute value properties. Yes.
Can't have composites because of the triangle inequality.
Yeah, the triangle inequality doesn't work if you try to do it with like 6 or something like this. What you have is you just end up with something that like breaks down. Because the problem is that you can't figure out what the absolute value and the absolute value of 2 and the absolute value of 3 would have to be. They would have to be sort of both less than 1 is the argument that you give, and then that causes a contradiction. So, all right. So we have, and then we have this. Not only do we have the triangle inequality, we have this thing that's sometimes called the ultrametric inequality, non-Archimedean bound. Now, so all right, half a step back. All right, great. We have all these absolute. We have these like absolute values, 1 for each prime, and then also the regular absolute value. You know, just the usual one. But that's it. There aren't any others. And this is the kind of thing that mathematicians would immediately think of as soon as we sort of stumbled backwards into cooking up these P-adic absolute values. The immediate next question is, okay, well, what else is there? And the answer turns out to be nothing interesting. So this is a result called Ostrowski's theorem. And so what it says is, if I have a non-trivial absolute value on the integers with this non-negativity property, it's multiplicative and it satisfies the triangle inequality. Then up to taking a power of it, which if you take a positive power of something with all these properties, it also does. So you might as well just assume that you normalize it, so to speak, by sort of resetting that. Then you either end up with just the regular absolute value, for real number, the one coming from real numbers, or you end up with one of these p-adic absolute values for a prime. That's all that you could have. And so secretly, that's why I made this list of properties that I wanted, because I knew this theorem before I started writing the slides. And I said, this is what I want to have happen secretly behind the scenes. Yeah.
Why you labeled it with 2?
Yeah, I did. Yes, I secretly labeled it absolute value with the 2 on it because it was the P-adic absolute value. See, I was lying after you figured that out before I said so. So that's the right way to do it. Okay. And then I have this little footnote about the trivial absolute value, which is the one that gives 0 and 0 and 1 and everything else, which if you like, you can check that satisfies this also. Yeah, it's basically like the 0th power of either of these, aside from having to resolve what you mean by 0 to 0, which in this situation is 0 and not.
Because by like, show you, it's a.
Yeah, 1 forces the absolute value to be 0, yeah. But everything else, you just take a sort of completely trivial absolute value. All right. Now, let's talk about sequences. And now comes the fun analysis / calculus stuff. It's good. Okay, so the idea, now that I have this nice absolute value function, I can use it to define a distance between integers. A new distance function, different from the regular distance function. Okay, so what do? I say the distance between two integers A and B is just the absolute value of the difference, right? That's how you define the distance between real numbers. So we do the same thing here. And this makes the integers into a metric space. If you don't know what a metric space is, take real analysis and then you will learn all about metric spaces. But metric spaces, the basic idea is it's a place where you can tell the distance between things and the distance function behaves in a sensible way. Let me tell you specifically how sensible. First, the distance between anything in itself is 0. Okay, I feel like that's a pretty sensible distance function thing. Second, the distance function is symmetric. The distance from A to B is the same as the distance from B to A. All right. And then finally, the distance satisfies the triangle inequality. So I mean, I didn't actually write it out here, but because I figured I would draw it on the board. Okay, so here's A, B, and C. And so the point is that the distance, this is the distance from A to B. And this is the distance from B to C. And the point is I want it to behave like a triangle inequality. So the sum of these two had better be like at least as big as the distance going straight there. And the idea is that those three properties turn out to characterize sensible distance functions. You can get a shitload of mileage out of these, just these three things. And to learn more, take some real analysis. All right. Or pay attention to the next 10 minutes of this talk. All right. So the purpose of having the distance metric is that it allows us to make precise the idea of convergence. Okay, to sort of talk about things getting closer and closer together. So suppose I have a sequence in a metric space with a distance function. I want to say, what does it mean for this thing to have a limit, to converge to a limit L? Okay, so intuitively, what does it mean if I have a sequence of numbers like A1, A2, A3, that converges to a limit? It means that the distance between my numbers and the limit goes to 0 as I go really far out of the sequence. Well, so I can just say that, right? I just phrase it in terms of the distance function for my metric space rather than the absolute value, which is what you would do for real numbers. And so I just say, yeah, the distance between an and this limit number has to go to 0 as I go far out of the sequence. Okay. So again, this is just generalizing the usual idea of a convergent sequence of real numbers. So now let's do it with the P-adic metric. So there are lots of trivial examples of convergent sequences I can give you, like 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, right? That definitely converges. It converges to 2. Okay, here's another one. 1, 2, 4, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, right? So a sequence, I can do whatever I want for a while. So if it's eventually constant, it certainly converges. Those are boring. Here's an interesting one. I claim under the 2-adic metric, if I take a n to 2 to the n, that converges to 0. Which is like, okay, if I take bigger powers of 2, they converge to 0. Which is like, well, no, they don't. They go to no. See, this is the difference. This is the 2-adic metric. The powers of 2 get small, and so it makes sense to kind of say, well, yeah, if they're getting really small, they should be converging to 0. But this follows just by doing this calculation with the distance method. Because I mean, I have it written down on the slide here, but I'll write it on the board so you can watch me do the steps. Right? What does it mean, like, to say the sequence 2 to the n converges to 0? That means if I take the distance under my 2-adic distance function from 2 to the n and 0, that this goes to 0 as n grows. Well, what is this distance? It's the 2-adic absolute value of the difference. Well, the difference of 2 to the n and 0 is 2 to the n. And then what's the absolute value of 2 to the n under this metric? It's 1 over 2 to the n. And so I say, well, what happens to the numbers 1 over 2 to the n as n goes to infinity? The point is that that goes to 0. Yes, very wonderful. And so the powers of 2 converge to 0. That's what I wanted. That was the whole point of this. Very encouraging. Okay, so it gets better though. Because like not only do the powers of 2 converge to 0, I can even add them all up. Right? Because what I wanted to do is I wanted to do 1 plus 2 plus 4 plus 8 plus 16, and that's supposed to be equal to -1. So if I'm really bold, maybe I think that like I just take the partial sums of that, and maybe that just converges to -1. Right? That's what that should mean. So let's compute them. Here we go. Put it over here. So what are the terms of my sequence? Well, I have 1, 1 plus 2, 1 plus 2 plus 4, 2 plus 4 plus 8, etc. Okay. So A, let's say AN is 1 plus 2 plus 4 up to, I think I did 2 to the n minus 1 for convenience. All right, so then you have to go figure out what this sum is, which is not very hard because it's 2 to the n minus 1. And if you've never seen this before, it's just an application of the finite geometric series formula. So if you just take this sum, double it, subtract the original from the doubled one, you get 2 to the n minus 1. So of course, 2s minus s is just s. So there you go. Okay. Or you can prove it by induction. Also a relaxing exercise. Like every problem that every formula that you write down and prove by induction. Okay. All right, so here's AN. So now I claim that they converge -1. So what's the distance between AN and -1? It's the 2-adic distance, 2 to the n minus 1, minus -1. That's the absolute value of 2 to the n again. Goes to 0. I just took that whole thing and I shifted it by -1. That's what that one was. Powers of 2, these are powers of 2 minus 1. So, isn't that great? This sequence of partial sums converges to -1. And so if I, quite reasonably, just define an infinite series to be the limit of the partial sums, which is how you define an infinite sum, now this statement is 100% legitimate. 1 plus 2 plus 4 plus 8 plus 16 equals -1. As long as you say sort of in little parentheses somewhere under the 2-adic metric. All right, pause to allow the audience to just sort of like let that wash over you. That like this is actually completely legitimate. Yeah, it's cool. Yeah. So don't let anybody tell you that that's wrong, because it's true. You just have to make sure that you're doing it in the right place, in the land of the 2-adic numbers. Okay. Now, I can also do this one for 9 plus 90 plus 900 plus 9,000. That also converges 2-adically to -1. And the point is, if you just write down the partial sums there, it's 10 to the n minus 1. But 10 to the n, powers of 10 also get really small 2-adically. Because, well, 10 to the n is divisible by 2 to the n. So the 2-adic absolute value of 10 to the n is also 1/2. And so that also goes to 0. So like we get 2 for 1 practically. Because we also get the one for the infinite string of 9s. That calculation is actually correct and legal as well. And it also works 5-adic, because you have 5 to the n here as well. So not just those two, 2 and 5. All right. But the original sum, right, when I plugged in r equals 10 to the geometric series formula, I like started by multiplying it by 9 so that I could do that carrying calculation. But the thing we really wanted was 1 plus 10 plus 100 plus 1,000, etc., which was supposed to be minus 1. Is there a way I can make that legitimate? The answer is kind of. So let me give you sort of directly, the answer is no. Because there's no possible limit value for this, for the partial sums of this sequence. The reason is if there were, right, it would be some integer. If I multiply it by 9, it would have to be -1. But there is no such integer. And so this infinite sum doesn't converge under the 2-adic metric to an integer. Secretly, it should be converging to -1/9. So that is not an integer. Okay. But here's where I, again, as a mathematician, say, well, why do I have to say converge this to a limit L? Why do I have to tell you what the limit is ahead of time? There are lots of other ways to talk about convergent sequences.
Do the thing where it has to, the space between terms goes to 0 instead.
Yes. There are lots of other ways to prove that a sequence converges. And another one of them is to show that it's what's called a Cauchy sequence, or Cauchy sequence if you're European. Okay. I had lots of European analysis instructors, so Cauchy sequences. So what's a Cauchy sequence? If you haven't seen this before, it won't be particular. I don't have time to make it particularly clear to you precisely. But the idea of a Cauchy sequence is the terms have to get and stay really close as you go far out. So the point is, a sequence converges to a limit when they all get close to some number L. A sequence is Cauchy if the terms all get close to each other. Okay, they all sort of cluster around. Okay. And the reason that this is so useful, and so you can prove one of the standard things you do with sequences of real numbers is prove that these are equivalent. A sequence converges to a limit L if and only if it's a Cauchy sequence. But the reason that having this Cauchy condition is so much more useful if you're trying to prove things about convergence is that you don't need to know what the limit is. You just have to know that the terms get really close to each other. You have to be able to estimate how far away the terms are from each other. It's sort of intrinsic rather than knowing what the limit is sort of ahead of time. Okay. And in fact, if you want to construct the real numbers, one of the ways that you should do this, the best way, in my opinion, to construct the real numbers is with Cauchy sequences. Right, so how do you get the real numbers? You start with the integers, because the integers are just handed down on a tablet. All right. And then you construct the rational numbers, which is easy. You just write down some equivalence classes of fractions, like I do when I teach intro to math reasoning, and also every day before I wake up. And then once you have the rational numbers, how do you get the real numbers? The point is that the rational numbers have lots of holes in between them. Like there's lots of stuff missing from the rational numbers. And so you say, well, you take all the possible convergent sequences of rational numbers. But you say, what does it mean for a sequence of rational numbers to converge? Because like if I take a bunch of things that converge to the square root of 2, square root of 2 isn't a rational number. So I can't pose this notion of something converging to the square root of 2 solely in the universe of rationals. And so that's where the Cauchy condition gets you out of the jam, because you can just say, I take a Cauchy sequence of rational numbers, and then say, yeah, okay, I want to use Cauchy sequences to fill in all the gaps. And so how do you do that? You just say, you declare two Cauchy sequences to be equivalent if their terms get sort of the distance between them goes to 0 as you go far out. In other words, they sort of have the same limit, so to speak.
So you can just use Cauchy sequence as your number and then like.
Yes, exactly. And then you just say, I declare the real numbers to be the equivalence classes of the Cauchy sequences. And then you prove that you can add and multiply and divide them and that it's all consistent. Which is a huge pain in the butt if you try to do it directly, but it's true. And someone did it once upon a time, and now everyone can just talk about the real numbers. Okay, so this process is called completion. If you have a metric space, and it works in any metric space, if you have a metric space, maybe there are some sequences that don't converge to a limit in the space. So what you do is this construction, and you just say, take all the Cauchy sequences, declare 2 of them are equivalent if they sort of get close together, and then define that new space. with to be the space of all the equivalence classes of Cauchy sequences. And that's where all your Cauchy sequences converge now. The completion, you filled in all the gaps. And the magic is, it works just the same if we do this with the P-adic metric on the integers. And the thing that we get is the P-adic integers, Z sub P. All right, now, I know, like a lot of you, when you learn group theory or when you will have learned group theory in the future, like you see this symbol and you're like, oh, that's the integers mod P. No, it isn't. It's the P-adic integers. We number theorists were here first with this notation. This is the only notation that you can use for the P-adic integers, C sub P. There are lots of other ways to write groups of order.
That means to enjoy the C mod PZ approach.
That's enjoy, I demand it. Yes. Okay, so let me give you a description of what this looks like for the P-adic metric. They're infinite base P expansions. They're basically like power series where your variable is P. And you just have coefficients, and the coefficients are all digits in base P. So they look like sequences in the form A0 plus A1P plus A2P squared, A3P cubed, etc. Where each of the AIs is just a digit, 0 up through P minus 1. So if you want to do this in the two adic numbers, it's just infinite binary sequences that you think of like this. Okay. Now, you can check, you can convince yourself it's not so hard that that is a Cauchy sequence. If you just take the difference between two partial sums, it's sort of a bunch of zeros for a while, so the thing is divisible by a big power of P. Okay. And so the terms, if you go sort of really far out, it have to be really close because they all have big powers of P in the differences. Okay. So it gives you a Cauchy sequence. It's more work to show that every Cauchy sequence is equivalent to one of those. That's a little harder. And also to show that all those sequences are distinct from each other, which is a little not so bad. You just take the difference, they have to differ somewhere. That gives you the difference. Like, you know, the difference is like 1 over P to the n. Okay. All right. And the nice thing is that you can also do all the usual like arithmetic operations with them. You can add these expansions, you can subtract them, you can multiply them, and sometimes you can even divide them when they have multiplicative inverses. How do you do it? You do it just like a power series, but then you have carries. You have carrying too. So if you want to add 1 plus P squared, P cubed to the fourth, and add that to 1 plus 4P, 2P squared, 0P cubed, 0P to the fourth, and P is equal to 5, just add the terms, coefficient by coefficient. And then, okay, I would get 1 plus 5P squared, P cubed to the fourth. But since this is base 5, right, base 5 digits, I'm not allowed to have digits of 5. If I have like 5 in the 5's place, I turn it into a 25. So I sort of just carry that over. Okay. So it's like power series, but with carry. That's the idea. All right. Multiplication is similar. It's just more annoying because you do the distributive law and then you maybe have a shitload of carries. And I was going to do a slightly longer example and just sort of display it up here, but there's a finite amount of room on the slide and it started overrunning the edge, as I think you see. So, but the point is, let's say I want to multiply out these two P-adic power series. I just take the first one and then I just multiply it by the successive terms of the next one, distribute everything out and collect terms. It's like multiplying out polynomials or other power series. The only extra step at the end is then I have to like do all the carrying if I have coefficients that are bigger than P. Okay. So that's what the P-adic numbers actually, the P-adic integers actually look like. And then you can even do multiplicative inverses sometimes. So I have this calculation here to show you that if you take 1 minus P and multiply it by 1 plus P squared, P to the fourth, P to the fifth, that comes out to 1. Which again, you just get a whole bunch of cancellation. But what that says is 1 over 1 minus P in the land of the P-adic integers is exactly the same as 1 plus P squared, P cubed, P to the fourth. That's our geometric series formula. And so in the land of the P-adic numbers, that's always leaked. And in general, you can compute multiplicative inverses exactly when the constant term is not 0. And if you know how to do multiplicative inverses of general power series, it's the same calculation. They're just a recurrence relation. It's just a more annoying because you have to deal with the carrying. So let's see. I have like what, a couple minutes? Something like that, all right. So let me tell you a little bit about where this came from. Try to close things down here. So the motivation for constructing and studying the p-adic numbers came from studying solutions to polynomial equations in number theory. So very classic, very, very general number theory problem. Here's some equation, find all the integer solutions, Diophantine equations. Here's one that maybe you've seen before. X to the n plus y to the n equals e to the n, Fermat's equation. Right? I mean, this is pretty hard to like write down all the integer solutions too. Well, it's easy to write them down. It's hard to prove that those are the only ones. Is a more accurate statement. So the point is that if n is bigger than 2, then the only solutions to this equation in integers are when at least one of the variables is equal to 0. And so Diophantine equations, solving equations over the integers. Big object of study in number theory for literally millennia. Thousands of years we have been doing this. Okay. So fundamental basic idea about how to solve an equation over the integers. Okay, well, there's a lot of integers, too many in some cases, to think about all at once. So what you can do is if you want to figure out what the solutions to this look like, you can try reducing it mod p for some prime. Because if it has a solution in the integers, then it has to have solutions mod p. And so then maybe what you do is you try to solve it mod p and see what the solutions are. And then maybe you do this for a bunch of primes and try to piece together the information mod p for different primes p. And if there are solutions, like for example, let's say you do this calculation modulo like the first 50 primes, and then put that all together using something called the Chinese remainder theorem. Something that you might get as output is that this equation has a solution that's congruent to 17 modulo some 60-digit number. And you say, maybe I think 17 is a solution to this equation. That's a good idea. Maybe I should try that. And so in a lot of cases, you can use that kind of mod p information to sort of reconstruct information about the solutions in the integers. This is actually a way that you can multiply integers faster than just multiplying them out and doing the calculation directly. Fun fact. Okay. So in particular, one specific class of equations like this is trying to find the roots of a polynomial, mod p. And there's a very standard way to do this, which is first you solve it mod p, and then you try to solve it mod p squared using the information mod p. And then you try to lift the solutions mod p squared to solutions mod p cubed. And you just keep trying to climb up this ladder. And the idea is, okay, if you can compute the solutions mod p to the n for some big power band, like if I know the solutions to my equation mod 2 to the 1 millionth, it's a little aggressive, but if I know the solutions mod 2 to the 1 millionth, that gives me a pretty good idea of what it might look like. Okay. So in addition to doing different primes, you can sort of climb up the ladder with a single prime as well. Try to kind of do both of those at once. Okay, now, why is this a good idea if you start with the solutions mod p to try to get the mod p squared? Because if you know what the solutions are mod p, any solution mod p squared has to reduce to one of the ones that you already found. Right? So if there's like, if the solutions are congruent to 1 or 5 mod 7, then mod 49, they have to be 1 plus 7 times something or 5 plus 7 times something. That's the only possibilities that would reduce to those things mod 7. And so then you just, plug that into your equation and solve it.
So the smaller set.
Yeah, it's a much smaller calculation because you only have 7 choices for A and 7 choices for B now. All right, and then you keep doing this. You sort of keep lifting. All right, let me give you a really simple example. Let's solve the equation x plus 1 is congruent to 0 modulo powers of 2. So that's like stupid. It's x equals minus 1, idiot. I know that. Okay. Let's finish off on this. Okay. I know. All right. Let's solve it mod 2. Okay, x plus 1 is congruent to 0 mod 2. There's a solution, x equals 1. Okay, now I'm going to solve it mod 2 squared. Well, the only solution mod 2 is 1. So the solution has to be 1 plus 2 times something. And the something that I can pick is either 0 or 1. There's only 2 choices that give me different things mod 4. So I just try both of them, and I say, oh, a equals 1 works. So now I get a solution, x equals 1 plus 2 mod 4. Now I look mod 8. I say, okay, well, it's got to reduce to this solution mod 4, so it's 1 plus 2 plus 4 times something, mod 4. And I look for what the something is, I try the 2 possibilities, and I say a equals 1 works again. So now my solution looks like 1 plus 2 plus 4 mod 8. And then I keep going. I am assuming that you can figure out that what will happen is that it's always plus the next power of 2. And so what you get is the solution of mod 2 to the n is 1 plus 2 plus 4 plus 8 plus all the way up to 2 to the n minus 1 mod 2 to the n. And the point is, if I sort of take that all the way off, see, it was perfect, like sound effects, right? Just sort of keep going. If I say, okay, it's 1 plus 2 plus 4 plus 8 plus da 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 plus 2 to the n plus da da da, sort of mod 2 to the infinity, whatever that means, then that would be the solution. Well, that's what Z2, the two adic numbers, are doing. That's exactly what that represents. If you think about writing this in base 2, it's 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and you just keep going. That's exactly what that two adic expansion is. What it's telling you is it's just telling you what this thing is mod every power of 2 all at once. That's what the two adic numbers are. And so the point is that it actually gives you the original solution, x equals minus 1, when you sum it up in the two adic numbers. It recovers that exact integer solution. All right. Anyway, so the point is that that was a really trivial example, x plus 1 equals 0. The point is that it works for basically any polynomial. It has this like horrible formula that I just copied out of my number theory onto this slide an hour and a half ago when I was getting these slides done. Okay, so let me just finish off with this, which is, okay, there's some horrible thing that involves the derivative of the function and it tells you how to find the next solution. And if you stare glossy-eyed at this thing, I have some statement about the derivative of this polynomial, and I get like some, the next value involves the like previous value plus something times like the value of the 1 over the value. It's some weird formula. I claim that this is actually something that maybe you've heard of. If you write down, I rearrange the formula for you. What it is it's actually Newton's method. What you do is you just take the tangent line to this graph of this polynomial equation and find where it's equal to 0. And that's your next guess. And so this weird lifting procedure that I'm doing, that I was working out for you, is actually doing Newton's method inside of the two adic numbers. How do you solve that equation? Take the derivatives, set it equal to 0, right? Good stuff. And so, in fact, this is secretly analysis again. Okay. All right, so there's so much more to say. Like the P-adic integers have an incredibly wide range of interesting facts about them. One fact I wanted to mention for anyone doing topology is if you take an open ball, x minus x0, e less than r, an open ball like this, just all the things of its P-adic distance away from something, every open ball is closed. And every closed ball is open. Why? Because what are the possible values of R where you get interesting behavior? You have like 1 over p, 1 over p squared, 1 over p cubed, etc. So if you want to make this a closed thing, you just sort of go a little bit above. And if you want to make it open, you just go a little below 1 over p. So for example, x2 less than 1/3 is the same exact set as x2 less than or equal to 1/3. Because you can't have anything whose two adic absolute value is exactly 1/3. And so every closed ball is open, every open ball is closed. So some other words and or phrases. ZP is compact. It's locally compact, which is even better. It's totally disconnected because of this thing. Like any point you draw a little that has nothing else near it. It's just, the only closed subgroups are sort of p to the n times the thing. So like z mod p, pz inside multiples of p, multiples of p squared. They have finite index. And so as a consequence, every closed subgroup is open. Yeah. Closed things are open, lots of open things are closed. Weird.
We love topology.
We love topology, but here, let me give you a nice easy one. So remember when I told you before that if you try to decide if an infinite series converges, that this is really annoying. There's all these stupid series convergence tests over the real numbers. For the P-adics, it's really easy. An infinite series converges if and only if the terms go to 0. I need one test. One test, that's it. Converges if and only if the terms get small, period. That's it. It's the only thing you ever have to check. Beautiful, right? Just like everything that you could ever want to like have to not learn anything. Right. And then finally, if you want to write down power functions by power series, you can do like the square root. You can try to do the exponential. You have to make sure that like the denominators don't grow too big, so exponentials are kind of out. But there are lots of other kinds of functions that you can define as power series, and they all have the same exact kind of analytic properties. It's a radius of convergence and whatnot, and it's just the p-adic radius of convergence instead of absolute value. All right, and so here I worked out some example that I grabbed from books about computing the square root of something p-adically. So you can kind of stare at that while I wind down. So thank you. Really enjoy talking about the p-adics. They're really fun. So, all right. Questions? I'm happy to answer questions. Yeah.
Can you say something about the p-adic rationals and access principle?
Oh, sure. Okay. So one thing that I didn't say is, so the p-adic integers are a ring, so you can add, subtract, and multiply. But there are some elements that don't have a multiplicative inverse, like 1 over p, for instance, which is kind of easy if you think about base p expansions. Because if you take something and multiply by p, it just shifts all the digits over. But it's not hard to make them a field. You just allow yourself to divide by powers of p. So if you're familiar with what Laurent series are for complex functions, it's the same procedure. You just allow yourself to have a finite negative power. And so what you get is the field, the p-adic field, Q. And then you can sort of do all of your usual field things. You can talk about field extensions of QP and do all of the things that one does in regular number theory. Sort of start taking that as your starting point for talking about.
Still a complete metric.
Yeah, it's still there. Like you could just define QP directly as the completion of Q under the p-adic metric. So how does the p-adic metric work on Q? You just sort of pick out the power of P. It might be a numerator or R. Yeah. Okay. Yeah. So it's if you complete Q, the possible completions are either these p-adic fields QP or the real numbers. So it's like those are the completions of Q, and sort of they all tell you different information. In some like a strong sense, when you talk about these completions, there's sort of the p-adic ones, and then there's the completion at infinity, which is the real numbers. So the real and complex numbers are sort of like behave kind of like a prime, just an infinite prime. It's kind of a philosophy of number theory. All right, and so then the other thing is, if you want to study a polynomial equation like this, another thing you could do is, which is much more trivial, is try to find the solutions over the real numbers. Obviously, that's, for most equations, it's kind of obvious whether there are solutions or not. But the really interesting phenomenon is, if you have a Diophantine equation like this, you're looking for integer solutions. It certainly has to have p-adic solutions on p for everything. And it also has to have real solutions, because you just take integers, they give you things p-adically, they give you things over the reals. A much more interesting question is, does it work the other way? In other words, if I know the p-adic solutions for all the p's and the real solution, do those things conspire together to force integer solutions to exist? And the answer is yes, sometimes. For quadratics. For quadratics, it turns out that this is equivalent. And this is like a fairly deep theorem of Hasse. And then for higher polynomials, the answer is no. You can give examples that are things that have solutions p-adically for every p and solutions over the reals, but no integer solutions. And understanding sort of exactly the nature of the obstruction, the difference between sort of knowing what happens at every prime and infinity versus what happens over the integers. This is like a very, very active area of research in number theory right now. The foundation of Selmer groups, if you're trying to study elliptic curves. There's all sorts of things. Brouwer groups in general, if you want to study number fields. And at least half of the recent fields medals, I would say over the last dozen or so years, for people who are in number theory, we're working on a problem of that ilk in some way or another. So it's a very, very active area of research, this idea. So this field, QP, is called the local field. You get it by localizing in some sense at the prime P. And it's the analog of sort of taking a power series expansion of a function centered at a specific point. It's the number theory version right now. Sort of isolating the behavior at this single prime and kind of ignoring what happens elsewhere. And so there's sort of all sorts of really robust and deep analogs between analysis and number theory and topology and geometry that all come in through these ideas. Anyway, good stuff. Other questions?
Can you do calculus in the P-adics?
Oh, absolutely. Yeah. I mean, this is like I have calculus right here. This is like computing a series expansion. This is just Newton's binomial theorem. So yeah, absolutely, you can do calculus. Like there's a whole theory of p-adic analysis, and there's a lot of, as one would imagine, sort of analogs between theorems from real analysis, complex analysis, and p-adic analysis. But the nice thing is that like p-adic analysis is usually easier in a lot of respects, and it actually has applications to things that don't look like they would have anything to do with p-adic analysis at all. You can certainly look up the p-adic numbers, p-adic analysis on Wikipedia or MathStack Exchange or something and follow and see if you can find some links. But there are some very interesting results that rely on p-adic analysis in a heavy way that don't sort of seem like number theory problems. All right. Other questions? Okay. Have a good weekend, everybody. I'm going to go home and do some more work. It'll be great.
Just a quick announcement before everyone heads out. Well, the first thing is, of course, you should take number theory next semester if you have perfect schedule. But the second thing is, thank you to all those who came to the course info session yesterday, where we talked about a bunch of advanced courses. We will be sending out the notes and the recordings to hopefully everyone, or at least it'll be posted on the Discord server. So if you missed it, but still want to learn about some of the courses that are being offered, the information will get sent out. And just as a reminder, a formal announcement will be sent out via email, hopefully this weekend. But there is a department social next Wednesday, or this upcoming Wednesday, I should say, at 4:30 p.m., 4:30 to 6 in 553 Lake Mall.
So if you missed the course info session, but still want to actually talk to the people who talked, go to that in the math lounge.
Highly recommended. There'll be pizza,
Wednesday.
coming out. Yeah.
Also, if I could take one opportunity, so they mentioned number theory 1, which I'm teaching in the spring. I'm also teaching advanced linear algebra, which is the best. Linear algebra is so great and useful. If you want to do anything involving science, engineering, mathematics, pure math, applied math, anything like that, advanced linear algebra is going to be your friend. And also, you do not need to have previously taken linear algebra. I start from scratch. It is proof-based, so take that under advisement. But it's a really, really good class.
Also, Sam, is there a meeting next week? Algebra and everything.
STEM engineering.
I don't know why they're on STEM.
I mean, I feel like maybe there's a brain where the science have been lost.
And if you like solving problems, come to the button.
Yeah, I think. I'm not excited. You can't. That's well, yes, but I can't be in advanced linear.